I'm Donna Arnold and I'm Senior Lecturer of Chemistry and Forensic Science in the School of Physical Sciences. One of my roles within the school is to conduct scientific research, and my team fits under the umbrella of the Functional Materials group. Functional materials form the cornerstone of our society and they play an important role in our everyday lives. From the clothes that we wear, the medicines that we take, and the electronics that we use for communication and for fun. For example, it's not so long ago that we saved data on one of these great big reels. Materials advancements led to us being able to save our data on this little tiny floppy disk, but it didn't have much capacity. As we've continued to move forward, we now save our data on these tiny USB keys, which have really large capacities, up to 8 or 10 gigabytes. Computers used to be the size of this room, and now we all have a computer in our pocket in the form of our mobile phones, and some of us on our wrist as our watch. So materials science is a funny subject. It sits at the juncture of many different scientific disciplines, including chemistry, physics, engineering, and biology. And as such, materials scientists are actively researching new materials for a magnitude of new areas, including renewable energy, batteries, solar cells, etc., medical diagnostics, and drug delivery, electronics, and smart windows, to name just a few. I am particularly interested in designing materials with specific functionality, the materials of the future. However, before I give you an insight into our actual research, let's take a step back and consider how and why we might want to do this. So if we consider a simple rectangular building block as shown here, how we stack these building blocks together and how we use them determines its functionality. For example, a bridge, a road, a building. It also dictates their properties. So for example, if we stack them in this fashion here, so they're all on top of each other, there's not much interaction between these stacks and the wall would be weak. However, if we stack them in a staggered fashion, such as this, our wall would be much, much stronger. We would overcome some of those problems. As materials scientists, we can use the periodic table to design building blocks. And then we can couple these together to design new materials. So if we look here, we can take a metal center here, shown in blue, and we can take 6 oxygens around it, shown in red, to form this octahedral unit. We can then couple this octahedral unit either through 1 oxygen, known as corner shared, or through 2 oxygen, as known as edge shared, to build new materials. Just as with our brick wall, how we stack these materials together, the structure that it forms dictates its properties. So for example, if you look onto the top right, you can see that the building blocks stack together to form these layers. These are good for electrochemical type of reactions, things that need charging and discharging, such as batteries. So layered materials are often good for batteries. One of our tools that we can use to change the functionality is the periodic table itself. For example, what elements that we choose to combine together will change the functionality. For example, we can replace our oxygens here that were in red with much larger organic ligands, as shown here. This increases the space of the cavity and makes materials that are useful for things like gas storage and detection. We can also change the metal center to be a transition metal with unpaired electrons. This allows us to have magnetic ordering in a material and we start to get magnetic materials. So if we return to our octahedral unit, we can couple it together here through the corners to form what is known as the perovskite structure. This forms a channel in the middle that another ion can sit in this case shown by this pink sphere. When the pink sphere and the blue sphere are ideal sizes, we form what is known as a cubic structure. That's a nice regular structure as shown on the left-hand side here. However, if we now change out the pink ion in the middle there for an ion that has a bigger ionic radii, it now doesn't fit in this channel very well. As a result, what happens is these octahedral units buckle out to make room for this cation to fit, and we start to get interesting properties. Things like electronic properties that are not shown in the cubic version. One other method that we have at our disposal to change properties is by changing morphology. Morphology describes the shape or the appearance of the actual particle, so not the structure, the actual particle of the material, a bigger three-dimensional structure. If we change the morphology, we start to change the behavior of our materials. So for example, on this slide, we have 4 different sample morphologies. So if you look here on the top right, you can see that we have a material that has very large spheres. However, on the bottom left, we see a material that has much smaller spheres, nanoparticles. And if we look on the bottom right, you can see that now we have a material that has a high surface volume ratio. It's made up of flakes, like cornflakes. This is really important as this also dictates the properties. For example, materials with high surface to volume ratios often show enhanced catalytic properties when compared to larger bulk particles. Small nanoparticles are also good for drug delivery systems. We need them to be able to pass through our body system, so they need to be small. So as you can see, it's important not only to understand what you're changing by changing the elements, but what you're changing by changing the morphology. So we have all of these tools at our disposal. So, how do we put all this knowledge to good use? In our laboratories, we're interested in preparing new multiferroic materials. Multiferroic materials couple together 2 or more of the so-called ferroic order parameters, which I'm not going to talk about here, but we're particularly interested in coupling magnetism with ferroelectricity in order to achieve useful magnetoelectric materials. So why would we want to do this? Well, if we first consider ferromagnetic materials, in ferromagnetic materials they have unpaired electrons, which we can align in the presence of a magnetic field. That means that we can point them all up, and if we alternate that magnetic field, we can point them all down. This gives us a way to measure binary code, i.e. 1 when they're all pointing up, and 0 when they're all pointing down. And this is how we form magnetic memory. If we now consider ferroelectric materials, they're analogous, except in these materials they now have an electric dipole. And we can line this electric dipole by applying an electric field, such that we can point all these dipoles up and have a 1 state, or we can point all these dipoles down and we can have a 0 state, allowing us to form ferroelectric memory. So why would we want to couple these 2 properties together? Well, magnetic memory is typically fast to load, but slower to save, whereas ferroelectric memory is the other way around. It's much faster to save and slower to load. So if we can combine these 2 properties together, we could effectively form a material that we could electrically write, i.e. save, and magnetically read, i.e. load. This would give us enhanced behavior over either the ferroelectric or the ferromagnetic counterparts, and higher processing speeds and lower power consumption. Our second motivation for working in these materials is that many ferroelectric materials are currently based on lead zirconate titanate. Lead is hazardous to health, so it's important that we remove lead from all of these materials. So it's important that we make lead-free multiferroics. Our work centres on the perovskite bismuth ferrite. Bismuth ferrite is arguably the most important multiferroic. This is because it's perhaps the only multiferroic material that shows both room temperature, electric, and magnetic ordering. The magnetism arises from the unpaired electrons on the ion. However, it doesn't order nicely in a ferromagnetic way as we would like. It orders in a much more complex magnetic arrangement. If we look here, we can see the bismuth, the purple ions. It has a lone pair, and this forces it to sit off-center in this perovskite cavity. This causes the formation of a dipole moment, and this is the origin of the ferroelectricity. However, there are many barriers to commercialization of bismuth ferrite. Firstly, it's difficult to make single phase. It has complicated magnetic structure, which is not exactly ideal, and it has poor electric properties in that it has high conductivities and high leakage currents, which make it not useful as a commercial material. Our research centres on trying to improve the properties of bismuth ferrite by using the toolboxes that I've highlighted today in my talk, by replacing different ions to try and improve both the properties. For example, we can replace bismuth with potassium. However, in order to maintain charge balance, this means that we also have to replace iron with niobium. As we increase the contents of potassium and niobium in the bismuth ferrite structure, we find that we make materials with excellent electric properties. However, this comes at a price. We lose the magnetic ordering. So now we're working on ways to keep this enhancement of electric properties, but also to maintain magnetic ordering. One of the other things that we're interested in is understanding bismuth ferrite properly. Why does it behave the way it does? If we can understand this, we can understand how to tailor the properties, what we need to do to design new materials. Our ultimate goal is to prepare designer materials that will power the future. Thank you for listening.